Okay, hopefully we are all back online. Ruben, thank you for your patience this morning. It was a bit challenging, but we heard that telecom is having some issues, so let's just bear with it and make the best of the situation. All right, so the questions that you had some trouble with was this number 4C, the fractional loss. Remember, when we talk about fractional loss, let me just please get my annotating tools in here. So when we talk about a fractional loss, this fractional loss, it is the difference over the original. So the change in over the original. So your power in minus power out, that's the difference over your original, your power in. Right? So if I then split this equation and say P power in over power in minus power out over power in, I get the following. Well, this should give me 1 because it's the same value. Minus. Now, in the previous question, what did we get? We got power in over power out is 1.85. And you say you've got that. That's fine. But look at this equation. It is power out over power in. It is the inverse. So if we change it, it is 1 over 1.85. And if we do that calculation, we get the 0.46. That's the fractional loss that we get. What we used to do, remember, if we said, what was it, percentage efficiency, basically, a very similar thing that we did in there, and it would just be times percentage times 100. I hope that makes a bit more sense. Let's move on to the next question that you guys had, and that was on page 6. Going to page 6 quickly. Moving to page 6. There we go. Just this is a bit problematic one. That happens, but there we go. So you asked about how do we get the x-axis in there? How do we get to this point? Well, remember, we have the sampling rate. If we have the sampling rate of 500 Hertz, it means there's a sampling taking place every 2 milliseconds. So that's the period that we calculate because we want it in this format. We want it in time milliseconds, so the period. So every 2 milliseconds, there is a sampling taking place, and this it gives these values, right? On the start 2, 5, 14, 4, 9, 11, and 7, the signal level that it gives. So you need to use your equation, your wave equation, to get to that. And try when you draw the graph, spread it to the maximum. So 10 blocks for each one. You would see I made a little tick every 5 to just count first of all. And yes, it takes a bit of time, but remember, this is worth 4 marks in the end. Okay, it is converting your digital numbers to your signal level. That also counts for a mark or 2. Then it is your x-axis and it is your steps, right? So also just a reminder, so this is going to, I'm not using a ruler. This is basically the profile that you are going to get in this question, on this graph, sorry. So the bottom part, although you can see I did solid lines in there, these you can have as dotted lines just to make sure you have it there, because if they didn't go down, it's not a histogram or a bar graph, right? So that should actually be dotted lines, just so that you make sure about that. Okay, hopefully that helped. Let's move on. Question number on page 7. Let's just erase all of this again. Going down, next page, your page 7b. Ruben, you had a question on this. Sinusoidal radio carrier wave has a frequency of the 900 kilohertz. That's your carrier wave, and an unmodulated amplitude measured to be 4 volts, right? Okay, the carrier wave is amplitude modulated by a signal frequency 5 kilohertz. For the amplitude modulated wave, determine the wave length. Remember, this is a radio wave. Radio wave is still an electromagnetic wave. So electromagnetic wave. And it's got the speed of light. So C be equal to 8 times 10, 3 times 10 to the power 8 meters per second. It's not 8, it is 8. That's 10 to the power 8. So we can, to use our wave equation, C, speed of light is frequency times lambda. We want the wavelength. So again, it is your speed divided by the frequency. Remember, speed and then frequency kilohertz is times 10 to the power 3, and that gives us a wavelength of 330, right? Hopefully that is good. I think that's the question that you had, the BI part there. Ruben, just want to make sure that I don't miss anything in there for 7BI. Okay, so that was that one. Let's move on to page 14. Wow, now this was a challenging question for me as well. I took a while and I went to the internet to have a bit of help, because it was slightly more than I expected from a 2-mark question. And it's not that bad, but wow, I can't tell you that it was an easy question. So let's look at this. Optic fiber is at length of 84 kilometers and attenuation per unit length of the fiber is at 0.19 decibels per kilometer. Okay, so if we then want the value of the attenuation in decibels, we need to multiply the 84 kilometers by the 0.1, and that gives us 16 decibels. That's our normal attenuation. Then they tell us the input power of the optic fiber is that, so it's my PM, it's my signal, and the output, at the output of the optic fiber, the signal to noise ratio is that 28 decibels. Now I want you to calculate the ratio for input power to the optic fiber to noise power at the output of optic fiber. This means you're working with 2 equations. So this is a bit of an explanation of how you get to the answer. You won't find that in a memo or anything else, so have a look. So normal attenuation for at the receiver there, at the transmitter, it's P in over P out, 10 log 10 P in over P out. The signal to noise ratio is the signal over noise 10 log 10. So if we look at that, remember now it's the sum of two logs, we can revert it back. These are your log rules. And we get to 10 log 10 of P in over P out times signal over P noise. But your signal is your output. Your power out and your power signal is the same thing. So those cancel out. And now you sit with a 10 log. Remember that 10 log just refers to the decibels. It gives it in decibels. So don't get just too worried about that. So they want the ratio in decibels. So that decibels actually means 10 log 10. That's what decibels. Right? And this is my power in, input power, over my noise power. So this gives me the ratio actually that they want over there. P in, this is P in over P noise. In decibels, meaning that. How did we get it? Well, it's the sum of my attenuation plus this, plus the signal to noise ratio. So it's literally just the 16 plus the 28, and that gives me the 44. So we actually worked back to see what do we need to do, because we have the two values in decibels. Is it the add or is it the subtract? In this case, it was an add, and we get to the 44 now to answer that. Okay, calculating the noise. Well, we have the signal power, signal strength, say power of the signal. We have the signal to noise ratio now, and you can calculate the noise power. This is the best how I understood it. Hopefully it makes sense to you as well. Right, let's have a look at this was page 14. Now you said page 16. Let's have a look. What is on page 16? It was challenging. As I said, many challenging things, but a lot of theory that you guys need to study in this chapter. Really a lot of theory. Let's have a look. Again, this is based on your theory. So we have a carrier wave of frequency 650, and your carrier wave always has a much higher frequency than your signal wave. Your signal wave in this case has 10 kilohertz. Your carrier wave has an amplitude of 5 volts. Right? Just gives you an indication of your amplitude, while your signal wave 3 volts. Now they say this carrier wave is frequency modulated. So your carrier wave or carrier wave's frequency will be modulated, changed according to your signal. But the amplitude is going to stay constant, right? So remember, if this is your, and I'm just referring back to your textbook literally in here, if you have your, I'm going to say carrier and signal, if you have your carrier wave and there's your carrier wave continuing through, you can see amplitude stays constant. Your signal wave has an amplitude of 3, so it's going to be slightly different, but you know, there is some different frequencies in there. When you frequency modulate, your amplitude of your resultant wave is still going to be the same as the carrier. What is going to be different? Well, the frequency is, it's going to be changed according to the frequency of your signal. So yes, That's going to be there, then there's going to be a larger one and a larger. Okay, I'm not going to draw it exactly like that, but I believe you get the point. So that 3 volt is not going to be applicable because the carrier wave was the constant volt. That's why the answer is 5 volt. If this was amplitude modulated, that would be slightly different. Then I believe it would be the sum of those two, because you're going to amplify it and decrease it. So it's going to be much different. Right. Maximum and minimum frequencies that you have in it. Well, they're talking about bandwidth. Right, so frequency of a carrier wave is modulated by the amplitude of the signal wave, by the amplitude. So what is the variation? If they tell us that the frequency deviation of a carrier wave is that 8 kilohertz per volt, and that is, sorry, the amplitude of my signal wave is the 3 volt per volt, that means we need to multiply the 8 by the 3, and that gives me the deviation in frequency. So that is actually 24 kilohertz. What does that mean, deviation? Well, it's plus minus 24. Plus minus 24, well, my frequency of my carrier wave is the 650. It's plus that or minus that, and that's why I get my 674 and 626. That's how it's manipulated. Okay. The minimum time between a maximum and a minimum frequency. I need to erase this to go down now. This is also not as nice, but we'll get a better way to talk you through all of this. So let's quickly have a look at what they mean in this question. They say the minimum time between the maximum and minimum transmitted frequency. Okay, so we have our frequency. What frequency is it? Well, it's the frequency of my signal. It's the T kilohertz. So now we have, if we do that and we apply our formula for period 1 over frequency, we get the time, but this time is between 2 maximums. So it's this time over there and there. This is not what the question asks. It asks the time between the maximum and minimum transmitted frequency. Well, so it's literally half a wavelength that it's asking. So it's this 1 times 10 to the power negative 4 divided by 2, and that gives me the correct answer. So a slight trick in that one. Okay. Hopefully that helped. Okay, guys, so that was communications. As I said, a lot of theory. Something that didn't come out that much in this worksheet was the difference between your geostationary satellites and your polar satellites. There's a few times that the question popped up in previous exams, pre-2016, where they ask you to compare the two or state advantages to disadvantages between the two. So I would just, Z-Notes has a very good comparison between the two. Have a look at that. If you don't have Z-Notes, I'll just post it on Moodle if it's not there yet. Have a look at it. Okay? And then, as was the end of this, but you need to go and study the theory. Definitions, you're going to save your butt in here, and then the power calculations. Right? So those two formulas. You don't get any equations in this chapter or topic. You need to study those. Right? So after this, we're going to move on to magnetic fields, but I'll give you some information as we move on to that. Okay, thanks.